So we'll go through that. So this will be our kind of our first example of, I suppose, quantum engineering, where we're going to use quantum mechanics to do something which potentially could be amazing. I don't know. I don't know like what the cutting state of the art is. I'm going to give you like the simplest scenario, and so in the end, it's like you're only transferring a tiny bit of information. So you're like, well, what good is that? And, so the question would be, can you scale it up and use something like this? But it does give a flavor of a lot of what you have to do and how a lot of quantum engineering works, like how you use quantum mechanics to do stuff. And so some of the tricks are kind of the same. Before I get started, so the goal for today is quantum teleportation. Okay, but before we do that, I want to just review, to kind of remind you of some properties of spin system, just because if you haven't looked at it in a while, or just so I kind of have it there at the ready. So we had the Pauli matrices, which represented spin. So in the normal basis where you make Z diagonal, does anybody remember what the matrix to represent spin was? First of all, Z is diagonal on the normal basis.
Is it 1 minus 1 on the
1 minus 1. Is it on the top? What about diagonality or off diagonality?
Diagonality.
It's 1 minus 1, 0, 0. That's in the normal standard basis. Okay? So basically, we're using states where I write plus Z is 1, 0, and minus Z is 0, 1. If I make these my basis states, then in this basis, spin in the Z direction is written in terms of this matrix. Okay? Fine. What about sigma x?
Is it just 1 minus 1 off diagonal?
It's off diagonal, but it's 1, 1. Okay? And sigma y it's going to be off diagonal, first of all.
I up top.
Minus I.
Minus I, and then is it another I?
Yeah. Minus I high is the way I remember it. And then the rest of it comes by, it has to be Hermitian, so you take the complex conjugate and the transpose, and it has to come back to itself. So you take the transpose, you get a minus sign, because they're equal and opposite, and the complex conjugate fixes that. Here, because it's real, the transpose, it is symmetric. Yep. All right. Now, what I want you to notice or remember is the following. If you take sigma x acting on plus z, so that's this one and this one, so you matrix multiply them, and what you see is that this becomes, we'll take a second to do that. So just multiply this matrix, or this vector times this matrix, 0, 1. It becomes the down state. All right, Marcus? Yeah? All right. Similarly, sigma x on minus z equals the plus state. So sigma x it just flips them up to down, down to up to down, down to up. Okay. We're not going to use it, but you could also do something similar. Y also flips them because it's off diagonal, but you get minus i's and i's everywhere, right? It turns out, so go through all that. Turns out sigma x, so I want to do, sigma z sigma x. So if I take this one, that gives me 0, minus 1, and so that gives me I times sigma y. All right? And I think we sell those a long time ago. The point is, if I have, we're going to have eventually get operations which are products of this, of these. You could actually make this look nicer maybe and collapse these down to and just use a single matrix, and it's going to be the third component. But I'm going to not do that so that I can keep everything real. But anyways, you'll see what I mean. There's a point where it'll look like, oh, sometimes you have like 4 Pauli matrices, but you could actually reduce it down to just 1, but then whatever. All right? So just remember that. If things get kind of, you ask, why does it look so gross? Well, you could make it do with fewer matrices, but then you're going to get complex numbers typically. So I'm just going to write things so things stay real. Okay, these are the ones I want. Sigma x flips it. Sigma z, on the plus state, it does nothing because it comes out plus 1. On the minus state, it picks up a minus sign. So maybe I'll write that down just to remind you. That's actually what we mean by this. So note, sigma z on plus z equals plus 1 times plus z. So it does nothing. And sigma z on minus z, that gives you minus times minus z. There you go. It flips the sign. Okay, so sigma x changes plus to minus and minus to plus. Sigma z doesn't switch them. They pick up a factor of minus 1 on the negative state. Okay? All right. So then we have that. All right. Now, and the other thing. Well, okay. So let's talk about, what do we mean by teleportation? What would you mean? Okay. Well, think about a car. If you could teleport a car, you would mean that you start with a car here, and maybe you push some buttons, pull some levers, and then somebody in China, Japan, pushes some buttons, pulls some levers, and your car is gone, and in front of them is a car which is identical in every possible way. That's what I'm going to mean by teleportation. And you say, well, that's not so crazy. You could just drive it. Yeah. What I mean is, it starts here, finishes there, but it was never carried. It never went. Nobody ever mechanically moved it from point A to point B. That's the goal. All right. So that's what teleportation means for us. What we're going to do, or what I'm going to describe, is how you can teleport a qubit, or a quantum state, from here to there. And I'm going to choose a small state. To do something complicated, you may have to work harder, but it gives a flavor of it, of how this would happen. Okay. All right. Okay. So what we're going to do, and this is kind of typical for a lot of the applications of quantum engineering kinds of things. You're going to try to leverage the features which are specifically quantum mechanical and new to do something you could never have done. So this, and the main feature is entanglement. So having properties where, or states where there are correlations between things which may be spatially separated, so that that locally you can't see the whole thing. Somehow the information is dispersed, and that's going to be the thing. So we're going to use, what we're going to have is an anti-correlated bell pair. What we're going to do is we're going to produce, you have some particle, some system that splits somehow, right? And part goes one way, part goes the other, okay? So we're going to have over here an experimenter called Alice. I don't know why, but everyone usually uses Alice and Bob. Okay? And what we're going to do is we're going to produce, so everybody's getting some sort of a state. But the total state is not either bit, it's the pair together. And what we're going to do is prepare the total system in the following state. Right, A for anti-correlated and the minus sign because it's the negative combination in the superposition. Okay, now, what do I mean by this? The first part, it's going to be implied that the left label, or in a minute here, labels, will refer to Alice, because she's on the left, and minus, because Bob's going to be on the right. So what this means is, we aren't sending Alice a plus state or a minus state. What we say is, we're sending them a superposition of these. Okay, so, all right. So multiparticle states are it's some sort of a state. What this would mean is, all right, yeah, I should say that. What this means, this state alone, this would mean that if Alice measures spin, she sees a plus state, and Bob measures his bit, he gets a minus state. Okay, and technically these are called tensor product states, but it's basically Alice's information times Bob's information, and it turned to get things. Marcus, we talked about this last week in the EPR stuff, where when you write it as a product, that's kind of how you can make sure that things which are separate, at least when they should be decouple and be independent, do. And so that's kind of the motivation for writing it this way. It's also just the way that Feynman wrote in his, when we had that neutron scattering off a crystal, remember that example? And then, well, he had momentum position kind of information, and he had spin information. And as long as things aren't interacting, there's no magnetic field or something, they're just separate bits. And he kind of wrote it in the same way. It's the way. Okay, so, all right. So what you would do is you would sort of prepare states where one person gets up and down, and another person gets down and up, and then you would take linear combinations to get this state. This particular state you can show has, when you measure the total spin or total angular momentum, it has no angular momentum. And so this can come out of things like decays. Like you start with a system with no total angular momentum. After the fact, it still has no angular momentum. How that works out is that part gets plus and part gets minus, and then this turns out to be the combination that satisfies that. So that's really why you might focus on this. It might be easier to make this physically than other combinations. Now, okay, locally, Alice only can measure this, because this part has been sent off to Bob, who could be on Jupiter, Japan, and similarly, or this. So Alice can measure the first factors, Bob can measure the second factors. Neither of them can access both, because they are separated by distances, and it would, light can't, because of the information can't travel faster than the speed of light, and so you can't instantaneously know what's going on in both places. Okay? All right. So this is the idea. for an entangled pair. What we're going to do is the following. We're going to assume that we can make these kind of pairs, right? And when you do kind of quantum engineering, a lot of times, you have, what will happen is, we're gonna have a car, well, we don't have a car, we're gonna have a qubit that we wanna teleport. And the way we're gonna do that is exchange a lot of entangled other pairs, ancilla pairs, some of it, like extra, like placeholders in math, right? These are extra bits. And then what we will do is make local operations, which might mix locally the thing that I want with my part of an entangled, of some sort of entangled combination. And when I perform local operations on the important thing plus these extra bits I'm assuming I can produce, I perform my local information, and then that basically converts, it kind of dissolves the car state into the information of the entangled state, sort of ultimately, and that's how it kind of the information gets bridged and sent over to the other person. That's kind of the idea of it. And we'll see an example of that, but it's specific to just a really simple state. That's the idea. So for a lot of these, I don't say all, but a lot of these quantum engineering applications, you need to have some source of entangled states, and you need to be able to produce lots of them. And that's kind of an engineering limitation for why. I was just listening to a podcast, and they were saying, so I've heard that, in the past, if you could get, I don't know, whatever, let's say 50 to 100 working qubits efficiently, then you could essentially simulate, I think, all of chemistry on a quantum computer. The problem is, we don't have, our qubits that we can make, at least make a lot of them, tend to be noisy. So then the way you do things is you make a lot of redundant systems, and then, so you accept that you're gonna have a high error rate, but then you do something many times, and then you kind of, there are error correction machine, basically you make, but if you kind of go with the kind of average result over many, it's more complicated than that, but anyways, you somehow use the fact that as long as the error rate isn't too high, if you have multiple copies of the calculation embedded in these extra qubits, you can sort of work out. So that the estimate was now, though, the guy was saying with current technology, something like you might need like 1 million qubits, a million bad qubits to get the to do what you could do with 100 good pure qubits, and you're always going to have some badness in there. So it's a question of what you can do. And I think like right now, even in the newspaper, they talk about engineering with like 50 to 100 qubits is what they can do, but those are noisy ones. So that's the limitation. Like, can you get to 1 million? Can you really get to 1 million qubits? I don't know. So, anyways, so in this example, Alice and Bob are assumed to have an entangled pair maker. They pull the lever, it separates, sends out, and they would have done this in the past somehow. Okay? Now, what we're going to assume is that Alice is in possession of some other spin state, psi. Okay? This is my car that I want to teleport across the universe. Okay? For this example, it's just going to be a simple qubit, right? So it's not very much information. What is it? Well, it's an arbitrary vector, let's say, in the Hilbert space, or in the space of states. So it's given by some number a times plus z plus b times minus z. It's not very much information. What is it? How much can it be? Well, these are complex vectors. So a and b could be complex numbers, but they have to be unit vectors, so that's like one constraint. So it's actually 3 independent numbers. Right? So it's easier just to call and say, hey, here are the 3 numbers. It's more of a proof of concept, I think. And I think it's illustrative of kind of the way that you leverage entanglement more than the actual practical interest in this. Okay, so Alice has, so what information does Alice have? Alice has psi, and she has whatever part of this is hers, basically the first factor. Right? So that's kind of the information she has access to. And Bob only has his half of that, or part of that. Marcus, you had a question? No? Okay. All right, is that? Okay. All right, so the goal to claim that you have quantum teleportation is that Alice initially has this thing. Now, I should say, she just has a state. She doesn't know, she doesn't maybe know what the state is, she just has it. So what I wanted to say was the teleportation machine should be some sort of way to send anything. Okay? It's no good making a machine. You could say, okay, I want a machine which only sends a plus z state from here to there. Well, that's not so exciting because you just make a plus z state and say, call Bob and say, hey, I'm at a plus z state. And he just takes a magnet and filters and selects plus z. What we want is some sort of a protocol or recipe that she can take any state and then give him a series of instructions about, okay, push this button, push that button, and then her state, whatever it was sent there. And what we will see is, in fact, she, we'll see how it goes. All right. Okay, all right. Now, so that's the goal. An arbitrary state starts with Alice, stuff happens, ends up with Bob. Okay, so what we're going to do is the following. I'm going to look at the total system, or the total quantum state of all 3. So the total state is, okay, so it could be psi, 1 over root 2, I think I forgot that in the notes, 1 over root 2, psi plus z minus psi minus z plus z. Right? Remember psi was the kind of car state? Or, because I could write psi using a's and b's in terms of pluses and minuses, I can do that same exercise. So I can write this as 1 over root 2, and let's see, psi was a times plus z. All of these are going to be z states, so I'm just going to write plus plus minus, plus b minus plus minus, minus a plus minus plus, minus b minus minus plus. And all of these are z directions. Okay. Do you see where how I'm getting that? I'm just saying that psi was a times the plus state plus b times the minus state, a times the plus state, b times the minus state. And the rest of it, these factors are just going along, they're just floating through. Now, what just in this language then, what part of this does Alice have control of locally? What does she have in her possession? Which of these three factors? Well, Alice is going to control the first two, right? Because she has she controls this state and this part, this state and this part. So the first two are things that are local to Alice. I don't know, it gets to be too much if I add some more subscripts, but the first two are things Alice has. The other one has been sent to Bob on the other side of the universe. Okay, fine. So she can do that. Then what kinds of, remember, so what I kind of laid out the plan. The plan was to start with the good thing, the information you're interested in, psi, and then the entangled pair. And then Alice is going to be somehow make local operations, things that she can do locally. And we want to use that fact that she can do local things to somehow come up with a recipe to send the information to the other direction, to Bob. So what could she do? So Alice could perform the following operations. Well, the important ones are she can do lots of things. Things that she can do is she can, using magnets or what, each specific physical realization, you have different ways of doing it. But with electric systems, maybe you're applying magnets or, I don't know, other operations, which amount to applying things like sigma x on the first factor. I'm going to write like this: tensor sigma x. I think in the notes I don't. I think I wrote it out. So if I label these slots as 1, 2, and 3, this acts on 1 and this acts on 2. All right. In the notes, what I did, because when I wrote this up, I kind of thought we might be a little bit more formal with tensor products, and so I worked it out explicitly. I actually went through the tensor product, or I wrote the answer down in that language. When you take tensor products, there are two kinds of products for the vector spaces. There's a Cartesian product. That's what you're familiar with that. You didn't even know that, right? When you go from the x direction or the y direction, you put them together and you form the xy direction, the plane. And then when you add in the z direction, so you go from x direction, y direction, z direction, put them together, you get R3, 3D. So those dimensions add, right? You just keep that's called the Cartesian product, but the directions the number of dimensions are additive, all right? So you could do the xy plane, that's 2D, and then take the Cartesian product with the z direction, that adds 1, so you do 2 plus 1 gives 3. That's 1, right? That's Cartesian product. Tensor products don't work that way. Tensor products multiply. So when you do with spin states, you have two-dimensional spaces. If you do the tensor product of this one, if I do like this, plus minus 1 tensor plus minus 2. This kind of compressed notation is shorthand actually for this. If you don't put the circle, it's a Cartesian product. If you put the circle, it's a tensor product. So how many spaces could you have? Well, what you formally do is pair up every basis element here with every basis element here. So it's 4. 2 times 2. And if you do a third one, now that we've got the car, or the psi, now we're in this state, 0, I guess. So it's 6-dimensional space if you have 3. Okay. Well, it turns out when you form the Cartesian product, not just of states, you can actually form the Cartesian product, the tensor product of matrices. This was 2-dimensional. This was 2 by 2. This was 2 by 2. This thing acts on the tensor product space, which means it's going to be 4 by 4. And I just wrote those out in notes. Okay? I'm not going to derive that. What I'm going to do instead is just kind of tell you the results and kind of show how you can believe that. So it turns out there are two operations which are special for her. All right, this is tensor. Write all that. Yeah, better. Because I don't want you to think it's matrix multiplication. It's not. It's something else. It's tensor product. No, sigma z, sigma z. These are important for her because it turns out these operations, which are kind of combinations of things on psi and her entangled qubit. So she's going to mix the thing she's wanting to, the car, with parts of her part of the entangled pair. So she's going to mix these two. So she needs an operation which acts on both of them in a concerted way. It's not random operations, it's very special. So she's choosing an operation which will work on these, and basically the car is going to dissolve away, and somehow the information is going to be reconstructible for Bob. Okay? So it turns out, remember sigma x and sigma z, you can't on one qubit, or just, you can't be in a definite state of both. However, it turns out that when you intertwine them in just this way, and I should put a tensor product here, this combination and this combination commute. Okay? So it just happens that and commuting is the same as they could be, that measuring this does not mess up this. If they commute, you can know this at the same time as you know that. All right? It's not true on the separate factors. It's only when you do it together in concert that it's okay. All right? And so, now, what Emily showed is that if things, maybe you just claimed, basically, if they commute, they are, then you can have states which are simultaneously eigenvalues of both of them at the same time. That's what it means to be simultaneously measurable, right? If you can have definite value of this and definite value of this at the same time. Okay? All right. So what I'm going to do is basically write down, so remember, what's the dimensionality? The space of states that Alice has, which is what this acts on, is a 4-dimensional space, because it's the product of 2 times 2. What I'm going to do is write down 4 states, so linearly independent states, so they span everything, and show that they are simultaneously eigenvectors of both of these. That is enough to prove that these commute without using the explicit matrices. So I'm basically avoiding going through constructing the explicit matrix. I'm just going to give you the answer, show that there are 4 vectors for which are eigenvectors of these, and since the whole space is 4-dimensional, that's enough that it works. All right. Okay, so I'm going to call this thing OZ. It just means sigma times sigma. This acting on 2 factors. I'm going to call this one OX because it's a little faster to write that than the tensor product. All right. Okay, I'm just going to claim this. So now, I'm going to define new states, okay, plus, okay. This looks like the other one, but it's going to be a linear combination. This part is not, so these are states available to Alice. Okay? This state is not, this is not plus z plus, it's not plus z plus z. What this is plus oz plus ox. All right? And it's built, again, all vectors, you can take linear combinations, so you can use any basis. I can express this thing, which is going to have eigenvalue plus 1 under oz and plus 1 under ox. I can build it out of the original basis that Alice has locally, which is 1 over root 2 times plus z, plus minus z minus z. Okay, so how does that work? Here's what I want you to do. Apply OZ to this. Remember, OZ was sigma z tensor sigma z. And the first bit acts only on the first, and the second bit acts only on the second. Okay? So, all right, well, let's see how this works. If this one acts, what does it do on the first factor? Nothing. What does it do to the second factor? Nothing. Okay? What does this first one do to the first factor? It's a minus sign. But I didn't do just this. I intertwined the two, so I simultaneously apply the second one.
So it stays the same.
Yeah, and you both get a minus sign. You get double minus signs, which is the same with a plus sign. And so what you get is that OZ acting on plus plus equals plus 1 times plus plus. So, okay, so that's why this first one was a plus, because this was labeling the z part. What about OX? So that's going to be sigma x tensor sigma x. OX acting on plus plus. Well, the notation tells me it better be a plus 1. How does that work out? What does sigma x do to the first?
Change it to a minus.
Change it to a minus. So this first factor in the operator flips the first factor in the vector to a minus. But then I'm not just doing this, I'm intertwining it just right, so I actually do a double flip. So this becomes, so this becomes minus minus, but this one becomes plus plus. And so in concert, when you operate in concert, the overall, they swap, but it's the same vector. And so, yeah? Okay, now look at what happens though. If these two are correlated, meaning they're the same, plus plus or minus minus, then when you act with OZ, it will always be a plus 1 for OZ. Right? Because, let's say, and if they are anti-correlated, plus minus minus plus, you always get a net minus sign when you apply OZ. Similarly, for OX, if the superposition is a plus, then OX will be positive, and if the superposition is a minus, OX will be minus. So this sign controls this sign, and the same or different controls this sign, it turns out. Right? So I'm going to just write the states down, but that's You just go through, it's just the same process. You just act piece by piece, and you can get it, all right? So what I'm gonna write down is the following. And then I'm gonna get plus, minus. This part tells me they have to be correlated, always the same. So that's gonna be plus, plus. This one tells me that the superposition has to be minus. This one, then I could have minus for z, and that's 1 over root 2. This minus sign tells me that they are anti-correlated states, so they will have opposite spins. So then that would be plus z minus z, and then this tells me it's the positive superposition. Sorry, minus z plus z. And then this one is minus minus. It's 1 over root 2, and this will be plus z minus z minus minus z plus z. Okay, Marcus, is that all right? Are you feeling overwhelmed? I assume.
Oh well, yeah, but I understand what you're doing with the numbers, if not why you're doing them. So
Well, yeah. Okay, I will. When I read about this quantum engineering stuff, I don't understand why. I'm not a quantum, like that's not something, that's something I want to learn. I've been kind of reading a bit about it. When I read these out, the various algorithms, I don't have, how do I say this? I don't have an intuition yet for why, when do I want to entangle this one or not that one? Or when do I do this or not that? Or why do I use this basis or that basis? I don't have that with these things because really none of the, well, my experience mostly is not been focused on entangled properties for the most part. I mostly don't think about that or haven't thought about that. And that's exactly the part of this which is not, this is where your Newtonian everyday intuition fails you. So to me, it's like, I can work out, so that's kind of where I am. I've worked through various algorithms, there are various factoring algorithms or this and that, and you work it out and you can see it works. But then when I take a step back and I say, well, why did you use this gizmo here and not that whiz bang there? And I don't know. Whereas when you think about a car, it's like, well, this part's spinning too fast, so you need some sort of component which is going to slow it down. Okay, so you choose a ratio of this to that. Oh, okay, so my local, even though I'm not an engineer, my experience with just physics and local interactions lets me kind of have a gut feeling like, okay, well, this has to happen, so, right? I don't have that kind of gut level feeling for why. I'm just going to show you this algorithm works. All right, that's about all I have at this point. Okay, but it does seem to be, the pattern is going to be, though, you have these entangled pairs, you have this information that starts out locally, and we're going to process this information. And what I think always seems to happen is you want to sort of intertwine make local operations that Alice can do to intertwine the information that we're interested in with these entangled pairs. You kind of intertwine them, and this is how we're going to do it, basically. We're going to perform, she's going to measure these, make these measurements of these quantities. And after you make a measurement, it's in a state of definite thisness or thisness, which means it's in this state. So she's able to make local measurements, which will, in the end, produce something in these mixes of the original basis vectors. And this is how these are, so she's going to make her local measurements, which kind of intertwine the information she cares about with the previously entangled information. And then what she's going to do is send instructions to Bob saying, take whatever you've got in front of you, do X, Y, Z, and then you're guaranteed to have the stuff that I used to have. So I don't have, as far as why this particular set, that has to do with technicalities of, I mean, there's a reason why you get OZ and not, why didn't I have OY, right? I assume you could have had OZ and OY. That would have worked too. But what you couldn't have had is OX and OY, right? But, so that I could kind of, that I have some feel for just through experience. I do know a little bit, but yeah, I don't have a gut level feel for this. I don't know if that helps, but that's just the truth of it. If I see a timing belt in an engine or a motor or whatever, I see a timing belt, I kind of know what that's doing. Right? I take my lawnmower apart, I can know, okay, this part goes here, this part, that part goes there. It makes sense. This doesn't always work that way, for me anyway. Okay. And now, I need my iPad because I got tired of writing and stuff. Okay, so here's the thing. This will be my crutch to make sure I have this. All right. So what we're going to do is remember our state, the triple state. This has all been in Alice's space. Now I want to go back to the total state, right? In the total state, psi, comma, a minus, right? That was everything. Before Alice makes any measurement or does anything, this is all of the stuff, her qubit plus the entangled pair just sitting there. This was 1 over root 2, and then she had let me write these all down here. So it was plus z minus z plus b minus z plus z minus z minus a plus z minus z plus z minus b minus z plus z. That's what I had at this beginning. Now, Alice alone, she sees this stuff. Right, that's the part that Alice sees, and Bob sees the third factor. And then on Alice's state, what I should have done here is, Alice can turn these states around, and she can say things like plus z for Alice equals 1 over root 2 times plus z, that's going to be, they're correlated, so it's got to be plus minus. These are the O, Z, O, X. O, Z, O, X. Notice it. Right? Again, it's just, these are vectors. You can take linear combinations thereof. So you can rewrite them for free. Nothing's changed. I'm just rewriting things. Right? It's just like tipping, just like in this room, I can tip my head and choose X and Y differently. Well, that's what she could describe the same state that way. But the real reason why she's going to do this is these are the operators, these are the measurements she's going to perform. And so she wants to rewrite the old state in a way that lets her pick off information in terms of the basis she's going to measure in. So if you're going to make a measurement in some basis, you typically want to rewrite the state in that basis so that you can kind of see what happens. All right? So she can go through and write, plus z, so everything's got to be correlated, and, so you could do minus minus. Those are correlated, they're the same, so it's going to be plus on the first factor, but it's going to be minus on the second factor. So it's going to be, it's going to be the difference. It's going to be 1 over root 2 plus minus minus minus. And similarly, plus z minus z, that's anti-correlated, and it'll be the sum, turns out. So it's plus, it's anti-correlated, so it's got to be part of the minus part, plus minus minus. And then the final combination would be minus plus. So it'd be minus, comma, plus, minus. I hope I've got these right. If not, you can check the type notes, but that's how it goes. All right, so when you go back and forth from one basis to another, it's just linear combinations of this or that. So, just like in this room, if I start off with vectors, x and y, and then I decide, I want to make the 45-degree line the diagonal, or the x basis, or, a new x basis, x prime. Well, it's just the sum of these two. It's just, you just add them in equal amounts and you get something along the 45-degree line. So the new basis vector is a linear combination, which is a sum, and then the y direction is going to be the difference in that case, the new y direction. So that's literally all I'm doing is I'm just adding and subtracting along 45-degree lines, and that's why you always get a root 2 everywhere. But it's in this abstract vector space, not the normal xy basis vectors, but the math is actually the same. All right? And then after you get your new basis, you can re-express the old basis elements in terms of it. So this is my original plus z basis. I don't want to measure z. I want to measure these kind of intertwining operations. So I need to rewrite this old basis in terms of my new basis. So these. Okay. So basically, here's the plan. Take these, rewrite these using these four, and keep track of the coefficients A, B, and they're going to get jumbled up. Okay. Doing this on the board on the fly, I'll probably screw it up. Yeah, I think I better not. I'll just copy from my iPad. Do you see what I'm going to try to do? So I started with this basis. I had these new operations which intertwined. I identified bases which are special for those operations, and I want to rewrite this original vector in terms of the new vector. That's all I'm doing. Okay. It's really just a matter of, it's just linear algebra. It's just a bunch of adding together little bits. I'm just going to transcribe from my notes. So it turns out, in terms of the new intertwining operator basis, this becomes you can rewrite this. Remember, these are scalars, they're complex scalars, so you can regroup them. You could just multiply this after the fact. you can push them around because they're not part of the vector. They're just numbers. And so you can kind of regroup things, and you can write it like this. This is Alice times something for Bob, which is A minus Z plus B plus Z. Plus minus A minus Z plus B. Maybe that can't be right here. I must have fouled the minus now. Sorry. Plus minus. This was a minus. This is a plus. And then I get minus 1 plus 1 tensor minus A plus Z. Oh shoot, this was a minus Z. Yeah, this is a minus Z plus Z plus B minus Z. These little factors are things you do on your own. I'm always looking over your shoulder because there are lots. It's a lot of little minus signs of this and that, and I'm just all I'm doing is making substitutions and regrouping and with common factors, and you just gotta the minus signs are really the devil there. So now I'm going to get minus minus, right? Because I've got plus 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 minus minus plus minus minus, and you get minus A plus Z minus B minus Z. Okay, I think I've got that right. That's right. All right. So what have we really done? Really, we've just done linear algebra. We've just taken linear combinations of basis vectors, but we chose to rewrite our initial state and describe it in terms of a basis which is connected to measurements Alice could make locally that would intertwine the interesting state psi with her part of the qubit, the entangled qubit, or sorry, the entangled pair. All right. So now, and these two operators commute, so you can measure OZ. She can measure OZ, and she gets a result. I don't know, +1 or -1. Fine. But because this commutes with OX, then knowing this does not mess up this, the robust. So she could measure this, get an answer, say, oh, okay, write it down. Say, sir, get that one. And she can measure this. You could get +1 or you could get -1. She picks that one. Okay, fine. So what happens? So initially you have this state. When she makes a measurement, after she makes a measurement, after the fact, it's in this state, +-.
So then you only pick out the term that corresponds to the measurement you made.
Yeah. So these were the possibilities beforehand. After she makes the measurement, she knows that she's in this bit. In which case, what does she know that Bob has in his hands? That. Remember, because of entanglement, operations that happen in one place affect the state on the other side of the universe. Her choice of these operations and measurement means that she knows that in Bob's hands on the other side of the universe is now this state. Bob doesn't know that. Bob doesn't even know if she made a measurement. But she does. Okay? Now, in order for Bob to end up with the same state, Alice has to call him up and say, hey, Bob, here are some instructions. If you do these steps, the thing in front of you will be what I started with. And Bob's not going to make a measurement. So he's not making a measurement. Because if he makes a measurement, it'll pick off, basically you'll end up with this or this, not this combination. So he's going to apply a magnet or something, or twist a system or whatever, but he will, without making a measurement, he will allow it to evolve in such a way as she tells him, basically turning on magnets and things. And then he will know that, even though he doesn't know what state it is, he knows that it's the same as what she had. That's what's going to happen. Okay? All right, so how can you do that? Well, now we're basically home free. Okay, so we just have to come up with a protocol. So so Alice makes some measurement, and she decides, is she here, or here, or here, or here? So she knows that Bob has this, or this, or this, or this. Okay? Now, I'll put it here. Well, all right. So let's think about that. Remember, what was the original state? So basically, how do we turn this into A plus Z plus B minus Z? How could you do that? Well, which one's the easiest one? I think this one's the easiest one. Yeah, the plus signs. This one's the easiest. What could you do? Well, look at that. It's almost right. What's wrong with it? Emily's going like this. What does that mean?
They're swapped around on the
They're swapped around. Gee, what could I do that would turn pluses to minuses and minuses to plus? By what? Sigma x. Right? So let's say, it's like for this one, this was actually the easiest one. She calls him and says, hey Bob, apply sigma x. So he arranges his magnets and does that, whatever. It's not a measurement, because he never actually measures a state. He doesn't measure this. He just applies some magnet, or effectively, actually, it's like a rotation. That's what it really would do. So he just twists the system, whatever. He's got some things that he can do, and that will turn this state, and this would become would be a plus, and it would swap them, and it would work. So here's the protocol. Then. This is the goal. The goal, well, we know what the goal is. So for this state, she calls it up and says, hey Bob, apply sigma x to this. Whatever your qubit is, apply that. And then you have exactly what I started with. Here, she says, okay, what do we need to do? Well, the first thing we need to do is get rid of the minus sign. Okay? What do we have that could get rid of minus signs or change minus signs? Sigma z. The problem is sigma z only changes minus signs on the minus state. So what you could do is first flip it, then put a minus sign, and let's see, so we flip it, this becomes plus, that's good. This becomes a minus, and then put it, so she could say, okay, Bob, apply sigma x, then z. You read them from right to left. So first apply sigma x to flip it, and then apply sigma z. And she says, oh, hey, Bob, if this is what, so she finds plus then minus. She says, hey, Bob, what we need to do is, I want to get rid of that minus sign. So what we want to do is flip it, apply sigma z, and then flip it again.
So basically it's just different combinations.
Yep. That's it. And this one's going to be a 4. So you want to put a Z to get rid of that, flip it, Z again, flip it. So it's going to be sigma X, sigma Z, sigma X, sigma Z. And then you might say, well, why are you doing that? Well, it turns out you can write products of these. You can make, so this is sigma Y, and then that what's left will be, so this is sigma Y, up to I's. This will be sigma Y times X, which is actually a sigma Z with a, whatever. It doesn't, so you can combine these in different ways, but that's how that works. So what have we done? Well, Bob started out with this qubit, this car, this quantum car, if you want, and then it ends up over there, but it was never in between. Right? It's not like she put it in her pocket and walked over and gave it to him. It went from here to there without ever being in between. And so it's teleported in that sense. It doesn't violate causality. Why not? Even though it went from here to there and never in between, why isn't that a problem?
It's because she gave him the instructions on how to.
Yeah. She had to make a phone call, and that uses classical, normal, less than the speed of light transfer of information. So, now, the quantum state was affected instantly. But the information was not. Right? When she makes her measurement, immediately Bob has one of these in his hands. But he doesn't know which one he has. And so when Bob makes, Bob measures, any operation Bob does, he just sees random pluses and minuses. He doesn't know. He doesn't know if the pluses and minuses he sees are because she didn't make a measurement and it just was still a random combination or in a superposition. Or maybe she did make a measurement and he got plus or minus because that was dictated by the outcome of her experiment. He can't tell the difference. From his point of view, he just gets one, because with a quantum system, you make one measurement and the system is uncontrollably altered after the fact. So you don't get, so you never get to kind of go back and test a little bit of it now and then go back and pick up the rest of it later. Once you make a measurement, it's done. So you can't, from that one outcome, you can't deduce whether, you can't basically, from what that one measurement, you can't deduce the full state. And that's why it works. So even though the state, the wave function is collapsed everywhere after she makes her measurement, the information comes really with the telephone call. And then, which is fine, relativistically speaking. The other thing that kind of highlights a little bit is that when you have a quantum system, I should have said this more with the EPR video or even Bell's theorem video. The information in a quantum system is kind of more than the sum of its parts. So Alice can know everything about her bit, and Bob can kind of fully determine his bit, but they aren't able to measure the stuff in between. So the total system is kind of more than that. So it's kind of like reading a book. I don't know how to describe it. You say, well, what's the information in a book? You say, well, okay, you read each page and you say it's the words on each page. So the total information would be you go through each page and you add up the information throughout. But it's kind of like there are these entanglements, kind of like, I don't know, saying that there's a message encoded in the 4th character on the 1st page with the 7th character on the 3rd page with the 8th character on the 9th page with the... And so just by knowing the individual leafs, you are not getting all the information. And so it's kind of more than the sum of its parts and how it's intertwined. And so you can have these weird things where you can fully determine what happens here, and yet you don't know at all what happens there. And vice versa, you can state 100% what the total system is in, and yet not know what any individual person will see. That's like these entangled pairs. You can say the total system is 100% A minus, which was 1 over root 2 plus minus minus plus. Okay. You can say, I know for sure the total system's in this pair, in this state. And yet I can't tell you what either person will see. Half the time Alice will measure plus, and half the time Alice will measure minus. I can't say what Alice will measure. So it's just, that's why the intuition's so hard, because normally, I mean, well, Emily had me in physics, so I say this, what's the general strategy? Or Marcus, you're in electricity and magnetism. So the general strategy is you figure out what's going to happen for the little point particles or dots, and you play Legos, right? You just glue it together, and you say, oh, now it's a little cube, and I'm going to stack the cubes, add them up, well, now it's an integral, and then you get flux and whatever, right? You play Legos. And the information in classical physics is basically Legos. If you understand all the little pieces, you just stack them, and you get the whole information in the larger object. That isn't how quantum mechanics works, because there is information which is delocalized. The information is not localized on the constituents, on the Lego blocks. The information is it's kind of amorphous, and you can move it around in different ways, but and that's why it's just different. So, anyways, I think that's kind of, I don't know. I mean, I'm not an expert in quantum information theory or quantum computing, but as I read through the different examples, to me this seems kind of prototypical in the basic strategy. You're going to use entanglement, and then you sort of make local operations which kind of interweave the starting information with the entangled stuff, and then it sort of gets migrated over somewhere else. And so, and then it's really, you're really careful in what you measure. You remember, notice Alice did not measure either. She didn't measure spin Z. If she had measured spin Z, it wouldn't have worked. She asked questions, kind of subtle questions, which don't ask about I don't know, how do you... So things like with quantum error correction, you don't ask, is this the right answer? What you ask is you create all these pairs. You don't ask, what answer did you get? Because that would actually, that would count as a quantum measurement and would destructively affect the system. Instead, what you do is you say, oh, not what is this one. Instead, you make a measurement which doesn't measure what the state of the little bits are. What instead you do is you say, are they the same? Yes or no? And so, and it turns out that doesn't count as a measurement sometimes. And so by asking slightly different questions, which don't interfere or destroy your system, then you can kind of say, well, okay, is this qubit the same or different than all these other ones? If it's different, there's some protocol for how to make it the same. You don't actually know if it's right. You just know that it's the same. And so then but then that's helpful, because then all you have to do is get, if you have a large group of them, and it's kind of basically say, is this one the same as kind of the average of these, yes or no? If the answer is no, you flip it, and as long as your error rate isn't too bad, you have a way of basically taking something which was imperfect and forcing them to kind of like a regression to the mean. Like you basically you make them perfect. That's how quantum error correction works. And that's why you need all those redundant copies. But it's all these, you have to ask the right question. And I don't have a lot of intuition for that. All right. So that's kind of, I don't know. That was kind of my last example. I don't know if that was too much or not, but that's kind of how these things usually go, I think.